Access to information is something we all need in both our professional and personal lives. Typically, that access is provided through similar methods, regardless of the purpose, but being able to access it in the first place is only part of the equation. Data must also be recoverable in the event of disaster. In this course, I'll cover authentication and disaster recovery concepts, beginning with the AAA framework of authentication, authorization, and accounting. Then, I'll cover important methods used to protect access to information, including passwords, PINs, multi-factor authentication, and biometrics. Finally, I'll explore fault tolerance, high availability, the importance of storage location, contingency planning, and disaster recovery concepts. Upon completion, you'll have built upon a foundation for the basics of IT. This course helps to prepare learners for the CompTIA IT Fundamentals, or ITF Plus certification exam FC0 U61. In this presentation, we'll provide an overview of the AAA framework, which refers to authentication, authorization, and accounting, three primary aspects of information security. Now, we'll take a look at each component in just a moment, but collectively, they work to provide controlled access to computing resources, enforce policies, and audit usage, and, if necessary, bill for services. And this framework is used by many organizations as the basis for all network security management. So, beginning with authentication, this process is used to control who has access to network resources. And the key word here is who, in that authentication is always the process of establishing your identity, or more simply stated, answering the question, who are you, whenever an access attempt is made. Now, one of the most common ways to establish your identity is by providing credentials, such as a username and password, but other information can be used, such as biometric data, including fingerprints or facial recognition. But one way or another, in the AAA framework, anyone requesting access to any kind of secured resource must establish their identity before access is granted. Authorization, then, is the process of determining what a user can do with any given resource. Now, just quickly, the terms authentication and authorization might be used somewhat interchangeably, at least in day-to-day conversation, but they are not the same. As just mentioned, authentication simply establishes your identity, and that's it. Once that's done, authorization then specifies your level of access, or again, what you're able to do with that resource, which is typically determined and enforced through resource permissions or various types of network policies. For example, if you need access to a file on a network server, you have to first log into the environment, which establishes your identity. Then you're typically issued some kind of software-based token, which establishes your identity and which you can present when you later attempt to access a resource. So when you try to open a file, in this example, the server hosting that file requests that you present your token. Now, this all happens behind the scenes. You don't actually have to do anything, but doing so proves your identity to that server. But that in itself does not grant you access. The file itself will have permissions assigned in what's known as an access control list. So the hosting server will then search for your identity in the access control list, and if found, you're granted access. But that access itself may still be controlled. For example, you may have been given the read permission, but not the modify permission, in which case you're allowed to view the file, but you can't make any changes. So the level of access is determined by the access control list, which is often determined by either the owner of the original resource or a network administrator. So they're also often referred to as discretionary access control lists, meaning that access to that resource is determined at the discretion of someone else. But at the end of the day, authorization addresses what you can do with the resource, but you can never be authorized until you have been authenticated. The final component then is accounting, which can have a bit of a double meaning, so to speak. But in the context of the AAA framework, it primarily refers to the process of tracking network activity and determining which resources will be monitored. So it might be more appropriate to think of accounting as accountability. But in some cases, it is also used to monitor resource usage for the purposes of billing, hence the double meaning just mentioned. But in either case, it still refers to the process of keeping track of what is happening throughout the environment. In the accountability context, it's useful for auditing and investigations when needed because you can refer back to the logs. And in the billing context, it can be useful for justifying expenditures for various service usage or indicate the need to reallocate or acquire additional resources. Or conversely, it can indicate resources or services that aren't being used, so they could possibly be decommissioned and those funds could be allocated somewhere else. As for implementation, in some cases there is no specific software or service that runs. It's just more of a manual implementation or a collection of services. For example, in a smaller network that does have, let's say, just one dedicated server running Microsoft Windows with Active Directory installed, that server itself does provide all three services. It would allow users to log in for authentication. It supports access control lists for permissions to resources on that server for authorization. And it supports auditing, which can track the history of resource access for accountability. So, in that case, the AAA framework is essentially implemented by default. But there are cases where you might want a more specific implementation on a more specific resource, in which case a local database can be maintained directly on that resource to provide AAA services. For example, a wireless access point or a network router can maintain all three services to track which users are connected, at which times, for how long, and what activities they performed during that session. But the most robust implementations use a dedicated AAA server. Now, that said, the AAA framework is just that. It's a framework. In other words, it's not a specific application or a service that you just install or enable on the service. It can use a variety of services and protocols to implement the framework, but it will ultimately do so in a centralized manner. Meaning that the AAA server will handle a variety of user requests for access to a variety of different resources. But there is a primary protocol that is used, known as RADIUS, which stands for Remote Authentication Dial-In User Service. Now, the dial-in in that acronym is a bit of a throwback to the days when modems were used to gain remote access to a network, which is almost defunct, of course, these days, but it is actually a good way to explain how RADIUS works. Now again, this is only one example, but imagine a large organization with many physical locations, such as local branch offices. If users are allowed to make remote connections to those branches, then you can imagine that there would be a server in each location that is designated to accept those connections, which is fine, but in that case, each server would have to be configured to provide AAA services on its own. So users in Region 1 would connect to the Branch 1 server, and it would provide services accordingly. But then users in Region 2 would connect to the Branch 2 server. Users in Region 3 would connect to the Branch 3 server, and on it goes. So rather than configuring each server in very likely the exact same manner, a single server could be configured, let's say in the corporate headquarters, and users in each region would still connect to their local branch servers, but they would do little more than accept and maintain the connection. When it came to anything related to the AAA framework, those servers would simply pass those requests on to the central server in the corporate headquarters, and it would look after everything in that regard. So now you only have to configure one server instead of one at every branch. So this model allows you to simplify the overall architecture, and it provides centralized management of all AAA services. And it's not just limited to remote connections. Many other devices, such as the aforementioned router or access point, could also forward its requests to the Radius server so that it can also offload those responsibilities to that centralized server as well. It can also receive logs from all other devices that are participating, so that logging can also be administered centrally from the Radius server. And there really is no limit to the number of devices that can participate. As long as the server can handle the workload, it can provide AAA services to the entire organization regardless of size or geographic separation. In any case, if your organization needs a more structured approach to its security, you should begin by examining an appropriate way to implement the AAA framework in your environment. In this presentation, we'll take a closer look at the process of authentication and the role it plays in the AAA framework, which is primarily the assertion and affirmation of the identity of a user or a device. As a simple example that doesn't even involve technology, if I'm traveling and I have to board an airplane, this involves authentication because I have to present a photo ID to the gate agent, which establishes my identity by listing my name, which is the assertion part that says I am Aaron Sampson, but my ID also includes a photograph, which is the affirmation. But no matter the method or implementation, authentication is always the process of verifying that a user or a device is who or what they claim to be. Now, in the case of a user, one of the most common forms of authentication is by entering a username and password. And there are other acceptable methods that we'll cover in a moment. But with this approach, again, the username is the assertion of the identity, and the password is the affirmation because it's assumed that we are the only entities that would know the password. So coming back to some of those other acceptable methods, they can be based on three main factors: something a user knows, something a user is, and something a user has. Now, any or all of these can be used in any combination, so you aren't limited to just one factor. And if you do implement more than one, then this is what's known as multi-factor authentication, which is significantly more secure because more than one method of affirmation must be supplied before authentication is accepted. For example, it might not be all that difficult for a malicious user to determine your password, but if another factor is required, such as facial recognition, then the password alone is of no use. Things that a user would know include a password, a PIN, or the answer to one or more security questions. But of course, the key here is that only the user in question should know these values. Now, I'm certain that most of us are familiar with using any or all of these, but for as prevalent as they are, passwords, PINs, and security questions aren't all that secure. Depending on the service or environment, password requirements might not be all that strong, and many of us like to use common characteristics such as birth dates or names of those who are close to us, and the answers to security questions are common targets of phishing scams and other types of social engineering attacks. So if you are relying on the factors that you know, be sure to keep them private and don't use values that can be easily determined by others. Something a user is refers to physical attributes of the person in question and include their retinal pattern, their fingerprint, their face, voice, and/or signature. These factors are generally regarded as being unique to each person, and they remain relatively constant throughout our lives, so they're quite useful at affirming our identity. With the exception of the written signature, these factors are also commonly referred to as biometric data because they all refer to biological characteristics that can be used to aid in establishing our identity. And lastly, something a user has refers to a physical object such as a security pass, a hardware token of some kind, and/or a mobile phone. Now, the implementation of any of these can certainly vary. For example, the security pass could be something as simple as an ID card with a photo, or it might be a smart card, which is a card about the size of a credit card, but with an embedded chip that can be detected by a reader, commonly used to open locked doors. Hardware tokens can take many forms, but flash drives are commonly used. When access to a file or service is requested, the flash drive would contain specific information and must be inserted so the information can be read. Or it might even have a small display screen which will generate a code that must then be entered. And similarly, a phone could receive a code via text message that must also be entered to gain access, or the phone itself might contain information that can be read by a near-field communications reader. Many of these factors, over and above a username and password, are becoming far more commonly used these days, particularly the things that you are. In fact, if you have a mobile phone right now, I'd guess that it's likely that you can be authenticated through facial recognition or by a fingerprint. And if you live in an area with bridges or toll passes, then it's likely that you have some kind of a security pass which provides your identity and payment information automatically as you drive through the toll gate. Regardless of the methods though, and or which factors are being used, authentication in and of itself remains the process of asserting and affirming your identity. But the more factors you require for that process, the more secure it will be. In this presentation, we'll provide an outline of the various methods by which authentication can occur. And again, authentication itself is the process of asserting and affirming your identity. And it's always required as the first step whenever access to any kind of secure resource is required. Now, perhaps the most common form that almost all of us are likely familiar with is called single-factor authentication, whereby a user need only satisfy a single requirement to be authenticated. Now, the most common implementation of this is by providing a username and a password. And by that description, it might sound as though we've provided two pieces of information. But the username is simply the assertion of identity, in that I'm claiming to be me, but it's the password that provides the affirmation, because I'm the only entity that knows my password, or at least I should be the only one who knows it. While this is perhaps still the most common implementation of authentication, single factor is not overly secure, so it should be reinforced with stringent rules, such as requiring the password to have a minimum number of characters, and that it use a mix of upper and lowercase letters, numbers, and symbols, which is referred to the complexity of the password. And users should be required to change their password periodically. The rules are all designed to increase the security of single-factor authentication because if your password was very short and very simple, such as 12345, it would be very easy for someone to guess or otherwise determine. Conversely, multi-factor authentication is so named because it requires more than one method for the authentication process to be successful. A common implementation of this is when you sign into an online service, probably still using a username and password, but then that service also prompts you for a code that is either sent to your mobile phone or to your email address. This is far more secure because even if someone does obtain your username and password, without the ability to receive the code, the username and password on their own are of no use. Now, since two factors are quite commonly used, you may also hear the term two-factor authentication simply because two is more specific than multi, but either term is appropriate. In higher security environments, however, there may very well be three or even more factors required, but for most of us in day-to-day life, two is more than adequate. Other factors that can be used in the authentication process might include location information, whereby access will only be granted if the request is made from a specific location, which is typically determined by the IP address of the requesting device or the network address of the request, or perhaps by GPS location. For example, if the primary headquarters of an organization allows access to resources from outside its network, it might only be allowed if the request originates from one of the branch offices, in which case either the IP address of the specific device or the network address of all devices in that network would be known, and more importantly, known to be trustworthy. GPS data might cover a much broader area, but there are many services and applications that can set up what's known as a geofence, whereby you simply select any given area on a GPS map, and only authentication requests that originate from within the geofenced area will be accepted. Another common factor used with authentication is the security question, whereby the requesting user is prompted by the authentication service to answer one or more questions, the answers to which only the legitimate user should know, because you're the entity that chooses which questions you should be prompted with. Now, security questions are perhaps more commonly associated with resetting a forgotten password, but they're also commonly used in live phone calls with some kind of support agent because in those cases, there is no password provided. But they're also commonly used in live phone calls with some kind of support agent because in those cases, there is no password provided. But in either case, they're still used to affirm that you are who you claim to be. Another component of authentication is what's known as single sign-on, and despite the use of the term single, this is not to be confused with single-factor authentication. In a single sign-on configuration, it means that signing in successfully to one service also grants you access to another related service. In short, there is a trust relationship that is enabled and configured between the services. Therefore, once you sign into one, the other trusts that authentication so that you aren't required to sign in again when you request access to resources in the other service. A common example of this is a local network environment that also uses cloud services. In such environments, the cloud service can be configured to trust the local authentications so that any user who has been authenticated locally can access cloud resources without having to sign in again to the cloud service. Single sign-on provides several advantages, including permitting your users to work more effectively by reducing the number of sign-in requests that have to be made each time they switch from one service to another. Users do not have to remember multiple passwords because the trust relationship that is configured also synchronizes local passwords to the other service, including when you change your password locally. That change will propagate to the other service so that you don't have to change it twice. And it can ease the burden on technical support because they don't have to reset forgotten passwords twice when they are forgotten. So while authentication may take a variety of forms and use a variety of factors, one thing is always consistent: the fact that it simply establishes your identity. So be sure to protect whatever factors you do use to ensure that others are not able to authenticate as you. In this video, we'll examine passwords and PINs and the role they play in protecting devices and information. Now, I'm certain that almost all of us are familiar with the use of passwords because, quite simply, they're perhaps the oldest method of establishing your identity, at least in the world of IT. And even if you're new to IT, you have undoubtedly encountered an online service that requires you to enter a password. But despite their longevity, passwords alone can be risky if they're the only method of authentication being used, and this is due to the fact that in some cases, it's not all that difficult, particularly for an experienced attacker, to determine what a user's password is. In fact, earlier in my career during a security audit, I successfully guessed the passwords of 2 users on the first try. Now granted, this was a smaller organization that was not all that familiar with security practices, hence the review that was conducted, and there was no password policy in place, which typically enforces the use of strong passwords, or to put that another way, they prevent the use of passwords that are very simple and easy to guess. These days, almost every organization would have a password policy in place that requires users to create passwords that contain a minimum number of characters, which is usually set to 8 or more. That must also use a mix of lower and uppercase letters because almost all passwords are case sensitive, and must also include numbers and or symbols, with the basic premise being that a password such as uppercase Q, 5, lowercase t, exclamation mark, lowercase b, %, lowercase h, 1, is far more difficult to guess than Apple. Password policies also specify a regular expiration period, which forces users to change their passwords after a set amount of time, often between 90 and 30 days, but that can vary to quite a degree. Again, with the premise being that the longer you have the same password, the more time you give an attacker to figure out what it is. And some may require the use of passphrases instead of passwords, whereby an entire sentence can be used as opposed to just one word. The personal identification number, or PIN, is very similar to a password in that it's still a value that we supply for identification purposes, but they differ from passwords in their implementation in that they're typically used as an access method that is simply faster because it's just easier to enter maybe 4 to 6 digits than it is to enter a complex password. Now, that in itself might make it seem as though a PIN is not as secure as a password, but they also differ in their implementation in that a PIN is almost always specific to a device or an object. For example, you likely use a password when accessing something like an online service such as email or to sign into an online retailer and many other services. However, a PIN is typically used to gain access to the interface of a device such as a mobile phone or a tablet. So while something like a 4-digit PIN might be easier to guess than a 12-character complex password, PINs aren't meant to replace the password. They're meant to be used in conjunction with the password. For instance, if you do sign into something like your online webmail from your mobile phone, even though that service itself likely requires a password, many browsers and/or the service itself will allow you to remain logged in even after the browser is closed. Or even if you do sign out, the browser might remember your password so that you don't have to type it in next time. So if either of those are the case, and your phone is then lost or stolen, and the device itself is not secured with a PIN, then anyone could gain access to your online email. So by securing the device with the PIN, the fact that your email is still accessible on the device is of little consequence if the person who finds it or stole it cannot determine your PIN to gain access to the interface. The same holds true for something like your bank card. The PIN is tied to the card, so even if your card is stolen, it's useless without the PIN. And if someone finds out what your PIN is, it's useless without the card. Another form of password implementation is the one-time password, which is exactly as its name indicates, in that it is a single-use password that is only valid for a single login session. Once you sign out from that session, a different password must be used for the next one. Now, one-time passwords also differ from standard passwords in that we as users do not create them. The most common implementation is when we access some kind of service that is provided by some other entity, so it's the provider who generates the password. Then, when we need access, we supply an email address or a phone number, and the password is sent to us. It usually has a very short lifespan. In other words, it has to be used generally within a matter of minutes of the initial request. Otherwise, we'll have to submit a new request. But as long as we enter it within that time frame, we'll be granted access to the service. One-time passwords are useful when the provider wants greater control over access to the service itself, and perhaps more to the point, wants to ensure that users do not share their password with other users, allowing them to piggyback on their account. Regardless of the type of password and the proliferation of more advanced authentication methods, I'd say that it's likely that passwords will remain in use for quite some time yet. So be sure to observe as many best practices as possible to help keep your passwords secure. In this video, we'll compare and contrast software and hardware tokens, along with examining how they're used. So, beginning with software tokens, these are most commonly implemented in multi-factor authentication in the form of software that issues a time-dependent code, meaning that the code must be used within a certain time frame. So, as an example, let's say you sign into an online service that is using multi-factor authentication. After you've entered your username and password, you might be presented with an option as to how you would like to receive your code. Perhaps it could be sent to an email address or to your mobile phone. But regardless of how it's received, you must enter that code to complete the sign-in process, and it must be entered within a certain time frame or it will expire. Now, the lifetime of that code is up to the developer, but they tend to invalidate fairly quickly, maybe after only a minute or two. So, if the code is not entered before it expires, you'll either have to begin the process again or at least request a new code, which is usually an option on the sign-in page. Now, while this does increase the security of any given sign-in attempt, it can slow the process to a degree and result in many additional codes being generated for the same identity if you use it for a variety of services. So, another way by which software tokens can be used is with an authenticator app. And there are several available in the app stores of most major platforms, including 2FAS, which is Two-Factor Authentication Service, Authenticator app by 2Stable, Google Authenticator, and Microsoft Authenticator. So with these apps, they're typically installed on mobile devices, and you simply enter the accounts you use. So for example, with the Google Authenticator, you would enter something like your Gmail address. Then when you sign in to any Google service from any device, the Authenticator app automatically receives a software token, which then causes the app to prompt you to verify the sign-in attempt. And you typically just need to click on yes or allow or something similar rather than having to enter a code. So it simplifies the sign-in process, yet it still uses multi-factor authentication, which of course is more secure. So by contrast, hardware tokens can be used as part of the same process in that they're still used in multi-factor authentication, but the additional code that is required is generated by a small hardware device that is often in the form of a USB device that must be inserted, or it might just have a small screen on which the code that must be entered is displayed. If it's a USB device, then after you enter your initial credentials, the service would simply inform you to insert the drive to complete the sign-in process. Or if it's a fob or any other type of device with a screen, then the device will generate a code that is also time-dependent, and that code must be entered to complete the sign-in. Now, as for some of the pros and cons, the hardware devices are considered to be more secure because nothing has to be sent to you. The device itself generates the code. But of course, a small device such as a flash drive or a keychain-sized fob is easily lost, and they also require batteries. So if the device is lost or the battery dies, you won't be able to sign in. So software tokens are considered to be a little more reliable, but bear in mind in many cases you must also have your mobile phone with you, which can also be lost or stolen, and of course their batteries can die as well. But with software tokens, you're usually presented with other options as to how to receive your code. So if, for example, you can send the code to an online email address, then you could access that from any device. In addition, with software tokens, nothing needs to be purchased, whereas if you were relying on hardware devices in a large organization with possibly thousands of users, the costs can certainly add up, particularly when you factor in having to buy replacement devices for those that are lost and or damaged. And these days I would say that software tokens are probably a little more common since so many of us already have mobile phones now, but hardware tokens are certainly still in use due to their higher security. Of course, if you're a service provider, the choice is yours, but if you do want to increase the security of the services you offer, then either type of token can help to ensure that all sign-in attempts are more secure than just using a username and password. In this presentation, we'll identify the roles and features of biometrics and its role in authentication and protecting information. Now, to begin, biometrics refers to the physical characteristics of a user that are considered to be unique, and they also don't change throughout a user's lifetime, or at least not enough to invalidate the information they provide. As such, they can be very securely used for authentication purposes, and they're very difficult to replicate or spoof. During the authentication process, the user presents whichever physical traits are required, and that information is compared to the information that is stored by the authenticating entity, such as a server, and if the two values match, access is granted, and of course, if they don't match, access is denied. So the process itself isn't really any different than submitting a password, but of course a password can sometimes be easily obtained by an attacker, whereas biometric information is much harder to obtain because, again, it's a physical attribute of the user. Now, there are various attributes that can be used in biometric authentication, and whichever methods are used will certainly depend on the situation and/or the environment. For example, a DNA scan can certainly be used to establish your identity, and it would be very accurate, but it obviously takes a lot of time. So it would not be appropriate for something where immediate access is required, such as entry into a secure location or access to an online service through a login. DNA authentication, however, would be appropriate in something like forensic cases or other types of investigations. A fingerprint or even a full handprint, however, can certainly be used for much faster access because most readers can scan your prints almost instantly. And again, as far as we know, fingerprints are unique to each person, so they're very effective at establishing your identity. The same applies to your retina and/or your iris. We each have unique patterns that can also be used for rapid identification. Retina and iris scanners are commonly used when physical access to a secure location is required, but they can certainly be used for other purposes as well. Similarly, facial recognition is becoming a very common method of authentication, particularly for mobile phones, because they all have built-in cameras now, and the technology has improved enough that they can identify facial characteristics very rapidly. And again, of course, no two people look exactly alike. Although, it is worth mentioning that identical twins have been known to fool facial recognition applications. But if the level of security you need is fairly high, it's doubtful that facial recognition, at least on its own, would be used. It's more likely that something like a retinal scan or a fingerprint might also be required, because even in identical twins, there is enough variation in those characteristics to be unique, but it is something to consider depending on the situation. Signature recognition is also considered to be a biometric value, but these two can be forged easily, so it's doubtful you would see it being used in any high security situation, but once again, it might be considered in something like an investigation of some kind. Lastly, voice recognition can also be used to identify you, but it is likewise susceptible to being fooled by recordings, and even behavioral recognition might be used in some cases, which could include the gait of your walk or characteristics of the way you type, including speed and common errors, which tend to be fairly consistent among most people. Now, again, those characteristics would hardly be regarded as foolproof either, and you wouldn't likely see them being used for the purposes of gaining access to a secure resource, but many of these characteristics can add up, so to speak. So, in something like a criminal investigation where the identity of a perpetrator is in question, any or all of these attributes may be used in conjunction to firmly establish identity. But as far as an authentication system for granting access is concerned, it would need to focus on the attributes that are unique and can be identified quickly and easily. In this video, we'll provide an overview of authorization and its role in the AAA framework. And quite simply, authorization defines the set of access rules that are in place for accessing resources and performing tasks, and they're most commonly implemented by assigning those permissions and rights to individual users or groups. Now, just quickly, I'd like to address the difference between permissions and rights because they might sound similar and might even be used somewhat interchangeably in day-to-day conversation, but officially, permissions are applied to resources such as files, folders, or printers, and they define your level of access to that resource, such as whether you're able to just view a file, which is the read permission, or make changes to it, which might be something like the modify permission. But rights refer to the ability to perform certain administrative tasks, such as installing software, logging onto a server, or using remote access services to log in. Now, either or both can be assigned to either or both of users and groups, but they do have to be assigned separately. In other words, if I want you to be able to modify a file and be able to log in using remote access services, then I have to assign each of those separately. But as a more generalized description, authorization determines what any given entity is able to do in any given environment. Now, a common element of implementing authorization is the principle of least privilege, which is really nothing more than a guideline or a best practice. In other words, there is no checkbox that you enable that says apply the principle of least privilege, but it provides a guide, so to speak, with respect to controlling permissions and rights for users and groups by recommending that only the minimum level of access necessary to do their jobs be granted, and perhaps more to the point, that nothing beyond that be granted. Now, of course, what is deemed to be necessary for you to do your job may change over time. For example, you might get promoted from a junior to a senior administrator, but of course your permissions and rights can be increased accordingly. But until that happens, anyone's level of access should be limited to only that which is necessary, which of course helps to improve the overall security posture of your environment by ensuring that users are not able to gain access to that which they don't need. Not only does it help to control the user's access to resources, but if their system should become infected with some kind of malware, the malware itself will usually run with the credentials of the currently logged on user. So, if it attempts to gain access to a resource, but that user does not have access to that resource, then it's likely that the malware won't be able to access it either. Another very common approach to authorization is using what's known as role-based access, whereby privileges are still assigned to users and groups, but those privileges are defined by your role within the organization. Now, there can certainly be variances in the roles themselves depending on the organization, but as an example, anyone who is a network security administrator would have abilities commensurate to that role, such as the ability to assign permissions on resources to other users, reset passwords, and create or delete user accounts. However, someone who is a human resources coordinator would be able to access the payroll database and view and modify personal information of the employees. So again, it's your role within the organization that determines what you can do. Now that said, any given user can certainly belong to more than one role, in which case their abilities would be cumulative, in that they would have the abilities of each role to which they belong. Similarly, authorization and your abilities are also determined by the type of account you have, which provides a means to categorize user accounts. Now, these are very commonly implemented on desktop or laptop computers, and in fact, they are always implemented on systems running Windows. For example, they include the administrator, standard, or guest user account types. Now, in this example, these do only refer to accounts that are created on the local computers themselves, as opposed to network-based user accounts. And you may have encountered this if you've ever created an additional account, even on a home computer. During the creation process, you are prompted for the account type. And if you specify administrator, then that account is entirely unrestricted on that device. However, if you choose the standard account type, it is not able to perform certain tasks such as installing software or drivers, nor can certain system changes be made. Guest is the most restricted, and as its name indicates, it's generally only used for casual access, but guest accounts cannot access any files on the system other than those they create, and also cannot make any system changes at all. But like role-based access, your abilities are predetermined based on the account type. Rule-based access, as indicated by its name, controls access through a predefined set of rules that are typically established through policies, which themselves are defined by network and security administrators. And rule-based can certainly work in conjunction with role-based or any other authorization method. For example, if you do belong to a role that has been granted the ability to log into systems through remote access services, there may also be a rule in effect that dictates that those privileges are only allowed to be used during business hours. However, you might also define exceptions to the rule, such as if you're an administrator, in which case access might be available 24/7. So again, it entirely depends on the nature of the organization, but rule-based access is more commonly used to refine access control as opposed to defining it. Mandatory access control refers to a process whereby rigid policies are established by administrators with respect to access control, but the level of access is determined by a classification or a categorization of the resource itself. Now, access would usually still be dependent on who you are and or your role within the organization. In other words, it can still be combined with other authorization models, but your access level is still dependent on what the resource itself is. And there would be no option for you to access that resource in any other manner other than what is dictated by the policy, hence the term mandatory. For example, in a military installation, if a file is classified top secret, then your level of access would likely be dictated by your security clearance level. But it's the classification itself that determines the level of access. So let's just say that clearance level 5 would be required to access anything that is classified as top secret. And even then, whatever level of access is made available by having clearance level 5 would be rigid and unchanging. So no matter who you were, your level of access would be the same as anyone else with clearance level 5 for top secret documents. Similarly, if a document was classified as confidential as opposed to top secret, then maybe only clearance level 4 might be required, but it would still use the same approach. Lastly, discretionary access control refers to the fact that access to the resource is determined at the discretion of the owner of any given resource, or possibly still a network administrator. But the owner could be anyone, not necessarily a network administrator or a security administrator. But it basically means that there aren't really any strict rules or policies that affect how access is determined. There may still be some basic guidelines, but ultimately, any given entity can have any given level of access as determined by the owner or the administrator. For instance, if you create a folder or a file, you are the owner of that object, and as such, it's yours to do with as you please. So you can decide who has access and at what level entirely at your discretion. So whether those entities are the highest level administrators or the most junior level new employees, you can assign privileges however you see fit. Now again, you should still observe best practices such as the principle of least privilege, but it's still at your discretion. Again, any or all of these methods can be combined in any situation, but at the end of the day, authorization in any form is always about determining what the users in your environment are able to do with respect to accessing resources and performing tasks. In this presentation, we'll outline the characteristics of accounting and its role in the AAA framework, which is primarily to monitor activity in the environment and to record or keep track of the monitoring information. In other words, it's not just real-time monitoring of what is happening right now. It provides the ability to review activity after the fact to try to identify anything anomalous or perhaps something that might indicate a potential security issue. By implementing these types of monitoring and tracking practices, you can determine characteristics such as the amount of time users spend in any given session, which services are accessed most often or least often, and how much data is transferred during that session, all of which can be useful in helping you to determine what normal activity looks like within your organization. And this can be important from a security perspective because in many cases, it's easier to distinguish activity that might be questionable when you have a better idea as to what is standard. Other purposes for accounting include billing information, particularly if you're a service provider who bills based on usage, better determining resource allocation in your environment, analyzing usage to determine the most critical applications and services, and planning for capacity, especially if you're considering a move to a different platform or a different application, or if your organization is generally upsizing or downsizing. And with respect to keeping track of the data that is gathered, the most common method in that regard is by maintaining log files, which are quite simply stored records of the events that you are tracking. Now, most servers, devices, and applications will generate log files automatically, but there may be cases where logging has to be manually enabled because logging in and of itself can sometimes generate a lot of data. So some devices and services don't create log files by default. But even if the volume of logging data is high, in most cases you can set a maximum size on the log files so that when they reach that size, they simply purge out the oldest data in favor of the new. Or you may also be able to set a time frame in some cases. For example, you might be able to specify that you want to save 14 days worth of logged data. Like the size limit, once the 15th day is reached, day 1 is purged out, so you always have the last 14 days. This, of course, helps to keep the volume of data to a more manageable level, but be mindful of the limits, because if you discover that you need to investigate something that occurred more than 14 days ago in this example, the logs will not contain that data. So again, just be mindful of the settings, or have a place to archive logs if they need to be retained for longer periods. Log files are generated by default for most major operating systems, including Windows, Linux, and Mac OS, but in all three cases, the events that are logged are set by default, with the exception of security-related events, at least on Windows-based systems in an Active Directory environment. In those cases, administrators and/or security personnel can create their own more customized security policies, the results of which are stored in the security log. But even in those cases, the events that can be logged are still preset. You just choose which ones you want and which ones you don't. They also have default size and retention settings, so be sure to verify what those settings are in your environment because they may have been changed at any point. Other elements of accounting might include tracking your location. For example, delivery drivers might have their routes monitored, and web browser history may also be tracked to determine if users are spending too much time on social media sites or other personal use sites while they're at work. Ultimately, by implementing the various methods of accounting as part of the AAA framework, you can help to create a more thorough picture of what is and/or what has been happening throughout your environment. In this presentation, we'll describe the concept of non-repudiation and its role in protecting information. Now, non-repudiation actually began as a legal concept, and it most certainly is still used in legal matters, but its basic premise is to ensure that no party can deny their involvement in an activity. In other words, there are measures in place that can effectively prove your involvement. Now, there are a variety of ways by which non-repudiation can be approached, and we'll take a look at those in just a moment, but in the world of IT, the most common implementation is in email communications, whereby encryption and digital signatures are used to establish both the identity of the sender and the validity of the message content. For example, if a disgruntled employee were to send out confidential information to one of their competitors in an email, the digital signature on that message cannot be changed or tampered with, nor can the contents of the message due to the encryption. So if discovered, the disgruntled employee cannot claim that it wasn't them, nor can they claim that the contents must have been altered while in transit. Now that said, in this example, non-repudiation only addresses the identity and message content, it does not in and of itself address the monitoring that must be in place to capture that message in the first place. So in any situation where non-repudiation is required, it must typically be combined with activity monitoring and other accounting measures. Now, while that previous example is one of the more common implementations, as mentioned, there are other approaches, any or all of which can be combined to increase the strength and the security of your efforts. For example, video cameras are in place in many environments to monitor physical movements and activity, so of course the footage they capture can be used to establish a party's presence in any given location, including when you entered, how long you remained there, and when you left. So in my previous example of the disgruntled employee sending an email to a competitor, while they might not be able to deny the digital signature nor the contents, they could of course claim that someone else stole their credentials and logged in as them. In that case, the digital signature would of course be accurate because the correct credentials were provided. But if video footage were also available at the point where the message was sent, then this of course could also be used to determine their guilt if in fact it was them, or their innocence, of course, if the footage does show someone else logging into their computer. Similarly, there might be other footage available that shows the user as being in an entirely different location, away from their computer, providing an alibi that it couldn't have been them. Biometric data can also be used in non-repudiation cases because a person's presence in a secure location or the activity they need to perform might require the user to provide a fingerprint or a facial or retinal scan to gain access. So as another example, if the case in question involved the theft of a physical item that was in a secure room that required a fingerprint to open the door, then the logs from the scanning device and or the authenticating system would show exactly which fingerprints were provided and at which time. And since biometric data is very difficult to mimic or spoof, the user whose fingerprint was provided cannot deny that they entered the room at the time in question. Now that said, without trying to sound too much like an action movie here, bear in mind that the most determined of thieves could force a legitimate user to provide the necessary biometric data. But again, this is where something like video footage could also be used in combination with the biometric data, which would reveal that the legitimate user was in fact coerced. Now, while I already mentioned digital signatures with respect to non-repudiation, email is not their only implementation. They can be used in just about any situation where the authenticity of the source or the author of any type of data needs to be validated. So even if you just create a document that is ultimately circulated to others by any means, the original can be digitally signed so that it can always be traced back to its source. By contrast, if I just create a file and store it on a flash drive, then give that drive to you, and you then copy it onto your system and then pass that copy along to someone else, it becomes very difficult to know the actual source, particularly in the case of the copy you made, because that copy will actually indicate you as the creator of the file, not me, because the copy was in fact created by you. Digital signatures can also be used in conjunction with hardware-based tokens, which increases the security because if that hardware device itself is tampered with in any way, the token invalidates and the digital signature can no longer be used. Lastly, you can also implement the counterpart of a digital signature, which is the digital receipt, which, just like a physical receipt, establishes that a recipient did receive a message or other content, and they show that the message was sent from sender A to recipient B. So again, if the sender is denying that they sent the message in the first place, not only would the digital signature indicate that they sent it, the receipt would as well. So just like combining the digital signature with something else like video footage, there is now an extra piece of evidence in the form of the receipt. So, like many things in the world of information security, the more layers you apply to non-repudiation, the more certain you can be of what actually transpired. Now, just to quickly finish up, I do want to reiterate that if an attacker does gain access to the credentials of a legitimate user, then of course they can do just about anything as that user. And something like a digital signature alone would have no way of knowing that the legitimate user's credentials were being used maliciously. So always be mindful of the importance of protecting your credentials, and do try to implement multiple non-repudiation methods, because non-repudiation can also be about protecting people's innocence, not just establishing guilt. In this video, we'll examine fault tolerance and its role in protecting information. Now, there can be a variety of ways by which fault tolerance is implemented, and a variety of resources that can be configured in a fault-tolerant manner. So it's a fairly broad topic, so to speak, but its primary focus is to ensure that a system is able to continue to provide services in the event of a failure. So when that ability is critical to you or your organization, you should attempt to locate anything that represents a single point of failure, which simply means that if it goes down, so does the service, and determine if it can be implemented with fault tolerance. As a quick example, if you have a database hosted on a single server and that's the only active copy, then if the server fails, so does the database. So that would represent a single point of failure. So using the example of the database on the single server, one method of implementing fault tolerance is through replication, which is the process of creating multiple copies of the data. But to clarify, that does not refer to creating something like a backup, which does represent a copy of the data, but the difference between replication and backups is that replicated copies are effectively active, in that as changes occur to the original, those changes are immediately replicated to the copies. Something like a backup does not change once it's made. So if you were relying on only backups, then you would have to make a new backup each time the original data changed. Now, that might be fine in some cases because not all data changes at the same rate, and toward that end, replication can also be implemented at either the component level or the full level, so to speak, which in this context could refer to different tables in the database. For example, if it's something like an online ordering system, then new orders might be created all the time, so the data in that table would be changing very frequently. But something like the products table, which stores information about the products you sell, might not change very often at all. So you can in fact set up different replication mechanisms so that the orders table replicates immediately every time a new order is placed, whereas the products table might only need to replicate on a schedule, such as at the end of each day. But regardless of which data replicates and when, the primary goal of replication is to ensure that another copy of the database is available to be launched in the event that the primary copy fails, and that other copy should ideally be hosted on a separate server, in case it's not just a service failure, but a complete server failure. In short, the replicated copy is standing by, ready to assume the services of the failed database, and it would have the exact same data as the original, so nothing is lost. Another aspect of fault tolerance is redundancy, which is certainly related to replication, but in most cases, replication refers to data, whereas redundancy removes single points of failure with respect to hardware, software applications, and/or networking components. But in short, redundancy, as its name implies, simply means having more than one of something. So in fact, in my example of the replicated database, both replication and redundancy are being used, in that if the database is being replicated to another server, then the database itself represents the data that is copied, but the additional server I mentioned would represent the redundancy, as would the required software to run the database on that server. Now, while I just mentioned that data is typically made to be fault tolerant through replication, it can also be configured in a redundant manner to improve its reliability, which is most commonly implemented by a configuration known as RAID, which stands for Redundant Array of Independent Disks. Now, to be clear, RAID does not create secondary copies of data like replication does. So, coming back to my database example, if you need another database to be ready to go at a moment's notice, then you should still implement replication. RAID in and of itself applies at the level of the hard drive, and it's meant to protect data against the failure of a hard drive. So once again, if you only have a single hard drive and it fails, then all data on that hard drive is inaccessible. Now, of course, you can and should have backups that can be used to restore your data. But in a RAID configuration, multiple drives are configured so that if a drive does fail, your data remains available. Now, there are several configurations that can be implemented known as RAID levels, but perhaps the best example in this context is RAID level 1, which is known as disk mirroring. As its name suggests, whatever data is present on one drive is identically copied to another drive. Now, that in itself is effectively replication, but it's always entirely local to that system. And as far as your own operating system is concerned, it only ever displays a single drive to you. So in a normal configuration, for lack of a better word, if you just have a single physical hard drive in your computer operating as the C drive, and let's just say for easy math that it's 1 terabyte in size, then you do have a single point of failure in that if the hard drive fails, everything on that drive is inaccessible. But with a mirrored configuration, you install a second 1 terabyte hard drive, and all changes to the primary drive are immediately reflected to the secondary. But your system does not display a second hard drive in its interface, nor does it show as being 2 terabytes in size. You still only see a single C drive of 1 terabyte. But once the mirror is configured, if the primary drive should fail, the mirrored drive automatically takes over, and you still have access to all of your data. So the redundant hard drive is what provides the fault tolerance. The management software for the RAID configuration will report to you that a drive has failed so that you can replace it, but once you do, the data on the surviving drive is copied back to the new drive, and once again you have your fully mirrored configuration in place. Networks can also be made redundant by the implementation of duplicate devices or backup infrastructure to ensure the availability and reliability of your network services, particularly for those that are deemed to be most critical. So once again, going back to my database server, we can implement replication to create multiple copies, and we can implement redundant servers to ensure that any given copy can always be mounted on a different server. But if the network components between the clients and the server or servers fail, then that database is still unavailable. So redundant switches or VLANs could be configured. The server itself could have 2 network adapters installed, and more than one physical network path can be created so that there would be an alternate way to access that server even if the network itself fails. Lastly, power can also be a single point of failure. Even if you have implemented other redundancy measures, if the entire building you're in loses power, then nothing is available. So you can, of course, use backup power supplies such as battery packs or generators to ensure that at least emergency power can be provided until full power is restored. Now, that said, bear in mind that devices such as battery packs would likely only be able to provide power for a few hours at best, and while a fuel-based generator can continue to run as long as the fuel itself is available, they would likely not be able to supply enough power for something like a large office environment to operate at full capacity. But again, you can be selective in terms of which services are most critical and allocate resources accordingly. So again, fault tolerance has many implementations, but it all comes down to identifying where your single points of failure are, then determining the most appropriate method to address that possibility. But it's also worth mentioning that while fault tolerance is certainly a great feature, it can be costly because you're spending time, money and resources on components that are literally not used unless there is a failure. And even then, they're usually only temporarily used until the primary component can be resumed. So it's a little bit like insurance, so to speak. You're more so paying for peace of mind, but those expenses still might have to be justified. So always be mindful of considerations such as budgetary constraints before you rush in and make everything redundant. In this presentation, we'll compare and contrast high availability and fault tolerance with respect to how they're used to protect information. And I'd like to begin by stating that you might hear the two terms used somewhat interchangeably in day-to-day conversation, but in the strictest sense, a good way to think about the difference is that one is effectively the result of the other. In other words, in this case, high availability is what you can achieve by implementing fault tolerance. Now, we'll flesh that out a bit more in just a moment, but first, let's just look at some key aspects of fault tolerance, which is the implementation of redundant components so that in the event of failure of a primary component, a secondary or a standby component can assume the functionality of the primary. And that process is known as failover. When the primary component is restored, it can then resume its previous functionality, and that process is known as failback. And in many fault-tolerant configurations, failover and failback can occur automatically, but that can depend on exactly what it is that failed and the degree or the severity of the failure. Now, ideally, what you're always trying to achieve is effectively services that can function normally for as long as possible. But fault tolerance can be quite expensive, so for some organizations, their level of fault tolerance may only provide them with what's known as graceful degradation, which means that services either continue to run, but at a much lower level of performance, or they may only run for a short period of time, perhaps enough to ensure that all connections and sessions are closed before the service stops entirely, which can at least ensure that no data is lost. But of course, in this case, if services have stopped, then your availability is gone. Your service is no longer available. So then, high availability refers to the availability of a system to continue to operate without interruption for, ideally, as long as possible. And many service providers will advertise a guaranteed level of uptime to attract more customers. That value is often very high in these cases, as much as 99.999% of the time, which is often referred to as 5-9 availability, which translates into only about 6 minutes of downtime per year. Now, at the time of this recording, I would say that offerings of 5-9 availability would be rare, but even just 3-9 availability, or 99.9% uptime, allows for just under 9 hours of downtime per year. And in most cases, those periods of downtime are scheduled, and customers are notified in advance that the service will be down. And these periods are most commonly used for maintenance to help improve the system overall, which of course can translate into even higher availability in the future. But with respect to whatever the availability is overall, of course, fault tolerance can be used to achieve higher levels, but ultimately, high availability is only concerned with how much uptime can be achieved, not necessarily the individual fault-tolerant configurations that have been implemented. And in fact, high availability does not always rely on fault-tolerant hardware configurations. For example, in some cases, availability might just be a matter of personnel as opposed to hardware. But the implementation of high availability is effectively based on the determination of which services are deemed to be most critical, which of course is entirely dependent on the nature of the organization, but that is then contrasted with how much downtime is acceptable to determine the desired level of availability. Now, in a perfect world, of course, we would all want 100% availability, but that simply isn't realistic in most cases. But service providers do still strive to get as close as possible to 100%, but I doubt that you would ever see it as being advertised by any provider, because that would literally mean that their service could never go down. So then, based on those determinations, the level of high availability needed will usually dictate where features such as fault tolerance are most needed. So, a good way to think about each aspect is that fault tolerance focuses more on the individual components of a system, whereas high availability focuses more on the system as a whole. For example, if you're a large online retailer, then you need many different components to remain functional for that service overall to remain available. But the two most important would likely be the website itself and the database that stores all customer and ordering information. So even if we consider just those two, there would have to be fault-tolerant configurations in place for both the server hosting the database and the server hosting the website. So each one could be configured in something like a cluster, which is literally a collection of servers that are all configured with the same hardware and software, and they all have identical copies of the data that is replicated across all copies in real time, so that if one server of the cluster fails, others can assume the services of the failed server. But then, within each server, there might also be RAID configurations, which use multiple hard drives so that if any given hard drive were to fail, the data on that drive is still accessible across the other drives. So the implementation of clustering and RAID for each of the database and web servers represents the fault tolerance. But the collection of all of them working together to provide a service as a whole, which to us is simply the ability to go onto the site and place an order, refers to the high availability. So from my perspective as a customer, if I do go to that site and I discover that it's down, then it really doesn't matter to me which specific component failed. I just see a service that is unavailable to me. So high availability has been affected. So the provider must then discover where the specific failure occurred and determine if that component can be made more fault tolerant. For instance, maybe it was nothing to do with the servers, the clusters, or the RAID configurations. Maybe someone tripped a breaker on the electrical panel by mistake and the entire server room where one of the clusters resides lost all power. So again, fault tolerance must be implemented for each component. And the more effectively it can be implemented across all components, the higher your availability. Now, to finish up, it's also worth mentioning that fault tolerance can also be implemented purely to increase performance, which itself doesn't have anything to do with availability. For example, in the case of the online retailer, if the website were only hosted by a single server, then all availability concerns aside, that server simply might not be adequate to handle the workload, so it would perform very poorly. So by configuring multiple web servers in a clustered configuration or behind what's known as a load balancer, all servers can share the workload, thereby increasing the performance. But of course, since you now have multiple servers running, even though better performance may have been your goal, you also gain higher availability almost as a side effect, so to speak. So again, fault tolerance can yield more than just higher availability. So ultimately, high availability is the result of your fault-tolerant configurations. Again, they're very closely related, but generally speaking, fault tolerance is implemented to achieve high availability. In a previous video, we discussed the role of fault tolerance, generally with respect to hardware components and their ability to recover from a failure, and ideally being able to do so as quickly as possible. But fault tolerance on its own is simply the ability to recover from a failure. It does not necessarily mean that the recovery must happen immediately. There are certainly situations where recovery can be a longer process, but that's entirely acceptable as long as recovery can happen. So in this video, we'll take a look at fault-tolerant measures that pertain to data activities, so that the ability to recover lost data is always available. And one of the most effective ways to ensure that is through data backups. In short, hard drives, solid state drives, and in fact, any storage device is just a piece of hardware, and no hardware will last forever. So failure is not so much a matter of if, it's when. Now, that said, you may, of course, replace an aging device before it ever fails, but that, of course, still assumes that a failure will occur at some point. But replacing the hardware itself is a simple process. But if you don't have backups of the data on that device, then replacing that data is very much harder indeed. Now, when it comes to data backups, there are several methods that can be used, which depend on the characteristics of the data, including how much there is and how often it changes. A full backup will back up every file you specify every time the process runs, regardless of whether the original file has changed. So, of course, if a file has not changed since the last time it was backed up, then it really doesn't need to be backed up again. But full backups are easy to configure, and it certainly never hurts to back up a file again. But you can end up with a lot of files in your backups that are identical. So full backups can tend to take up a lot of space unnecessarily. So they're generally used when the amount of data is low, changes are fairly infrequent, and you might not be all that concerned with how long the backup process takes. The flip side of that is when there is a high volume of data to protect, the data changes more frequently, and the backup processes and/or the recovery processes need to be completed as quickly as possible. In these cases, you can use either differential backups or incremental backups. Now, I find the best way to describe the difference between these is to simply look at an example. So, for starters, both types first require a full backup, which acts as a baseline. So let's just go with an example of an environment that runs a backup at the end of each day. So on Monday evening, a full backup is performed, which backs up all specified data. Then on Tuesday, it's likely that not every file that was backed up had any changes. So if the file was already backed up on Monday and it didn't change on Tuesday, then it doesn't need to be backed up again. So both incremental and differential backups will only back up the files that have changed throughout the day on Tuesday. So at this point, there's no difference. However, on Wednesday, the same situation likely occurs, whereby some files have changed, others have not. So an incremental backup on Wednesday will only look back to the incremental that was performed on Tuesday to determine which files have changed, and it will back those files up. But a differential will still look back to the full backup on Monday, and once again back up all changes since Monday. The same thing would then occur on Thursday. The incremental would look back to Wednesday's incremental and only back up those changes, whereas the differential will still look back to Monday. In short, an incremental backup will look back to either the previous full backup or the previous incremental backup, but a differential will only look back to the previous full backup. So the net result is that incremental backups are usually faster and they contain less data in any individual backup set. Differential backups may be larger because there may be some redundant files and they might take longer to complete. So why then would we use differentials? Well, it comes down to the restore time. In our example here, if a failure occurs on Friday morning, then to fully restore everything from incremental backups, you need to restore the full backup from Monday, then all incremental backups in sequence up to and including Thursday night. But since differentials capture all changes since the full backup on Monday, then restoration only requires the full from Monday and the differential from Thursday, and you're done. So incrementals result in faster backup processes, but differentials result in faster recovery processes. So it just comes down to what is more important to you. And recall that not every implementation of fault tolerance demands immediate recovery. In some cases, if full restoration can be completed in a few hours or even a day, that is acceptable to the organization. Others may need much faster recovery times, but again, it depends on the nature of the organization. Now, there are, of course, other considerations with respect to data backups and fault tolerance, which, of course, begins with simply identifying which data needs to be backed up in the first place and determining where to store those backups. And for the sake of fault tolerance, at least one copy of the backups should be stored in a different location. Ideally, you should have one copy that is in the same location for fast retrieval if it was just the loss of a hard drive or a server. But if the entire facility was lost due to something like a natural disaster, then an off-site copy might be your only means of recovering your data. These days, backing up data to the cloud is very common, but that would also depend on the volume of data. But there are also third-party storage providers, or if your organization has many branches, then copies should be maintained at other locations as well. But the more copies you have, the more fault-tolerant your data will be. In other cases, you might only need to protect very specific files that would not necessarily require any kind of backup mechanism, which might be more common at the level of individual user devices, but other methods, such as simply making additional copies, sometimes will suffice. Again, as long as those copies are maintained with respect to changes to the original. Many operating systems offer a file history feature whereby snapshots of files can be made, and changes to the original are then tracked so that any version of the file can be restored. This helps to protect data not only against loss, but from corruption or accidental changes. For example, if multiple people have access to the file and someone simply entered something incorrectly, you could restore the version that was made prior to that error, and the incorrect data would be gone. For files that change frequently and/or need to be accessed from many devices, features such as synchronization can be used, whereby a cloud-based copy can be accessed from any device, but any changes that are made can then be synchronized to local copies across all devices. And archiving simply refers to moving files that are no longer needed off to a location where they can still be accessed if necessary. For example, sales reports from previous years would likely not be needed in the current year, but they may still be consulted periodically. So you still want them, but you don't want them taking up space on your primary storage device. Lastly, it's also important to consider the operating system when it comes to backing up data, because of course your OS can crash or become corrupted just like any other data. Now, most backup utilities and/or the operating system itself will include an option to back up the system information, but depending on the method used, that generally refers to what's known as the state or the configuration of the operating system. In other words, the backup process doesn't necessarily allow you to just apply the data to the hard drive of the system in question and then have the entire operating system be fully restored. It typically means that the system must, or at least should, have its hard drive wiped. Then the operating system must be manually reinstalled. But once the new installation is complete, rather than reconfiguring everything manually, the backed up state of the system can be reapplied, and it will then be fully reconfigured back to the state it was in prior to the failure. Now, that said, there are ways to simply add a single file to a hard drive which does entirely restore everything exactly as it was. This is a process known as imaging, which effectively duplicates every single bit of information on a hard drive. So you can wipe a drive that has been imaged, then apply the image that you captured previously, and it will come back exactly as it was simply by applying that single image file. But images do not account for any changes that have been made since the image was captured. So unless you re-image the system every time a change is made, images can quickly become outdated. Whereas if you're just capturing the state of the system as part of a regular backup process, then those backups will contain all system changes. So again, the best option would depend on how often the configuration of that system changes. One way or another, having multiple copies of any kind of data helps to increase the level of fault tolerance for that data. So always be sure to include your data requirements when determining the best methods to protect it. In this video, we'll examine considerations with respect to data storage locations and contingency planning when it comes to protecting information. beginning with the location of data backups. Now, there should always be at least one copy of your backups available to you in the local facility where the original data itself resides. This provides you with quick and easy access to those backups, usually costs nothing more than perhaps some additional storage devices, and it's very easy to implement. For example, if you back up some data from server 1, then that data could be easily copied over to server 2 or any dedicated backup server, or even to just external storage devices. But by having it in the same location, if it's just a matter of data loss only, recovery can be performed relatively quickly and easily. However, some potential downsides of local backups can include the possibility of losing all data if, for example, the entire facility were to be destroyed due to a natural disaster such as a fire or a flood. Likewise, if there were a security breach in the local environment, such as a virus, ransomware, or other types of malware, then all data could similarly be affected. Now, if you have offline copies, such as tape drives or external drives that are disconnected, then malware wouldn't be able to affect those, but other types of threats, including malicious internal users, could still result in the loss of data if such a user were to steal the backups. Cloud-based backups, then, are certainly becoming more and more common due to the fact that most major cloud providers inherently create their own backups of anything you store with them. And they also store those backups in separate locations so that the loss of any given location does not result in the loss of data. Now, this is all done by the provider, and it's done transparently to us. But some may give you the option as to how many copies you would like and how dispersed those copies are. Access to your data is certainly convenient because anything in the cloud can be accessed from anywhere, at any time, from any device, provided there is internet access, and the amount of storage available to any given customer is, in practical terms, unlimited. Now, the more you use, the more it will cost, but providers will just keep adding storage as needed to be able to meet the demands of their customers. On that note, cloud storage does have downsides, of course, as costs can become very high if your storage requirements are very high. And of course, since the data can only be accessed by using the internet, the speed is entirely dependent on the speed of your connection at any given location. Now, if you're more or less relying on cloud services as part of your normal operations, then it could generally be assumed that the speed of your connection would be relatively high. But an internet connection rarely matches the speed of a LAN connection, particularly if you're in a more remote area where the infrastructure might not be all that robust. So while there are pros and cons for both on-site and off-site storage, for the highest level of data safety, both should be implemented because, of course, on-site backups are, again, very easily retrieved, which translates into the ability to restore that data more quickly. But off-site storage protects you against the complete loss of all data in the event of physical disaster. So by using both, you cover all the bases, so to speak. So when creating a contingency plan for your organization, which in turn will likely dictate the methods used for data backups and recovery, considerations should include the response time necessary, meaning how rapidly you're able to return to full functionality, and the level of business continuity you require, which refers to whether the loss of data will affect your ability to continue to provide services. For example, if you lose a web server, but you have backups of the data, then you might be able to stand up another server and restore the data in, let's say, 2 hours, just for the sake of argument. But that's 2 hours where you may not be able to conduct any business at all, if, for example, your business is taking orders through that web server. But if you can implement that server in a fault-tolerant manner, so that there is a standby server available to assume the services of the failed server, then you might not have any disruption at all. And if the data on those servers is being replicated to each other, then you wouldn't even have to restore from backups, because the server that took over from the failed server could replicate any changes back to the original server once it resumes. Now, that doesn't mean that you shouldn't still perform backups, because you could still lose both servers in something like a fire. Communication services should also be factored in with respect to ensuring that the services you use to communicate can also be restored. But in these cases, sometimes it's more important to simply restore the service than it is to restore the data. A good example of that is email. In the event of failure, users may not care about their existing email in their inboxes. They know that all of that data can be restored from backups, but they might need to be able to at least send and receive new emails as quickly as possible, in which case you only need to restore the services of the mail servers, not the data, which can typically be done in much less time. Then, once services have been resumed, you can address the restoration of data later on. Ultimately, the disaster recovery needs in any given organization will depend on the nature of that organization, but be sure to consider all factors when it comes to ensuring your ability to recover from disaster as thoroughly and as easily as possible. In this presentation, we'll identify the roles and features of disaster recovery in computing environments, which is a process that defines a set of policies and procedures to be followed in the event of disaster, which should also include both natural disasters and those that are human-made, such as errors or accidents. Now, of course, the disaster recovery needs of any given environment will depend on the nature of that environment, so there is no single approach, nor is there any kind of one-size-fits-all method that will provide the ability to fully recover from every possible type of disaster. But the most important consideration is the definition and the implementation of those policies and procedures that are specific to your organization. Or another way to put that is that no organization should be operating without a disaster recovery plan. It should always be assumed that a disaster will occur at some point. So, formulating a disaster recovery plan should begin by prioritizing your assets, which ensures that you address the concerns that are most critical to your operations first. Then you should ensure that you have addressed your ability to restore data and the services you use, which typically depends on the data, but that's not always the case. Sometimes service restoration can precede data restoration. For example, the ability to access existing records in a database clearly requires that the data be restored before the database engine can be restored. But for something like email, sometimes you just want to be able to send and receive new messages. In other words, I don't have any immediate need to access my previous messages, but I need to send one right now. So the service can be restored first before existing data needs to be restored. But of course, at some point, they both need to be restored. In some cases, the entire site or facility can be the asset in question. For example, a hurricane might knock out all power across a very large region. So if your organization has other branches or service locations, then they might be able to provide you with the ability to carry on operations with as little disruption as possible. Now again, how quickly you need to resume services will dictate what kind of site recoverability you need. So recovery sites are typically classified as cold sites, warm sites, and then of course hot sites. A cold site has the space available to be used, but little else, so nothing is really ready to go. Physical equipment might need to be moved, and a significant amount of setup might be required before full functionality is available. A warm site would have the equipment in place, but certain applications might need to be installed, maybe even some operating systems, updates applied, and of course the data would need to be restored. But clearly, restoration would happen more rapidly than it would in a cold site. A hot site then, as you might guess, is ready to go at a moment's notice. All equipment, software, and services are in place, and data is actively replicated to the hot site in real time, so you wouldn't even need to restore the data. In some cases, a hot site can provide full functionality in minutes. Now, clearly, a hot site provides the highest level of resiliency, but they're also the most expensive, and the most administratively complex model to maintain, but it all comes down to what your organization needs. As for the policies and procedures you do formulate, they themselves are also subject to failure, so to speak, in that they may have missed something. So you need to do your best to consider as many ways as possible by which a disaster could affect your organization and shore up any weaknesses in the plan. In addition, things change rapidly in the world of technology, so your policies need to be regularly evaluated and tested to ensure they keep up with the changes that have been implemented. Clearly, it's of no use if your recovery plan dictates that you back up server 1 or application 2 if those resources have been decommissioned and or replaced by newer versions. You also need to ensure that your recovery methods will in fact work. In other words, you can't just write down, back up the data on server 1 and call it a day. You need to perform test backups and restore operations to ensure that those processes actually work and that you can in fact restore the data that has been backed up. Lastly, you need to ensure that you engage your employees in training to ensure that they know all policies and procedures that apply to them specifically. For example, one of the most common issues that I've encountered personally is users who store their documents directly on their personal devices, as opposed to in their server-based folders. The data on the servers is, of course, regularly backed up, but local user devices are almost never backed up. So if, or perhaps more accurately when, a user loses data due to the failure of that device, of course they come looking to administration to restore that data, only to find out that there's nothing to restore because their data was never placed on the server. This might also be applicable to compliance considerations because in many organizations, data must remain within the confines of the organization itself. So if users do keep local copies of data and their devices are mobile, then taking that data with them when they leave the facility might constitute a breach of compliance. Now again, all of that will depend on the nature of the organization, but the point is that users need to be aware of that nature and work within the framework of the disaster recovery policies and procedures to ensure that full recovery can be achieved. In short, the best way to ensure recoverability is to assume that everything will fail at some point, then to determine what can be done if or when that happens. And the more thoroughly you address those possibilities, the less likely it will be that losses of any kind will affect your ability to recover from those losses. For our final presentation of this course, we'll outline methods for recovering data and services after a disaster, which refers to the ability of an organization to fully return to the state it was in prior to the disaster. Although it should be mentioned that in some cases, a disaster may in fact provide a good opportunity to make changes. If, for example, an organization was considering changing to a different application, service, or platform, the disaster itself may have been the justification for making that change. But that notwithstanding, it can be useful to begin with some common recovery terminology, including failover and failback, which refers specifically to the implementation of redundant components that are able to assume the services of a failed component. When the primary component fails and services are moved to the secondary or standby component, that's referred to as failover. When the primary component is repaired or restored, returning the services back to the primary is known as failback. Now, in some cases, both failover and failback can occur automatically, while in other configurations it might require manual intervention, but that depends on the components themselves and the manner by which they were made to be fault-tolerant. Recovery time objective is a goal that specifies how quickly restoration can be achieved, such as 1 or 2 hours. A recovery point objective typically refers to a point in time up to which data can be recovered. For example, if a database server fails at 4 p.m., but a backup was performed at 3 p.m., then the best recovery point might only be 3 p.m. But that, of course, means that potentially an hour's worth of data would be lost. So you might determine that an hour's worth of lost data is not acceptable. So you might increase the backup frequency or use something like transaction logs in this example to get your RPO right up to the point of failure. In an ideal world, your RTO is as close to zero as possible, and your RPO is as close to the point of failure as possible. But not every organization has the same needs. Getting values to those points requires more time, money, and administrative overhead, so in some cases those perfect world values just aren't required. Data restoration refers to the use of backups to recover data that was lost or corrupted, and of course that's often a necessary step in terms of returning your environment to a fully functioning state, because in many cases data is the key aspect of the failed component. So it's particularly important in any environment that all data be backed up to ensure that you can recover when disaster strikes. In short, if you need it, back it up. Now, when it comes to backups, as just mentioned, it really comes down to simply ensuring that they're being performed regularly and that all required data is included in the backups. But when it comes to the restoration side, you should prioritize which data is most critical and, of course, restore that data first. For example, you likely don't need to spend time restoring sales reports from 5 years ago. They just wouldn't be needed right now. Likewise, you should prioritize the services that are most critical, such as email, phone, LAN, and internet access. So again, don't waste time and effort restoring a service that just doesn't need to be used in the immediate term. So for each of those components, some examples of important data assets might include financial information, client and employee information, and product and process documentation. Now again, those are just a few examples. What's critical to any given organization will depend on the nature of that organization. But the key is to focus on what is needed right now, not what might be needed days or weeks from now. Lastly, service-wise, you should create an inventory of all systems and service accounts that would need to be restored in order to restore functionality, and identify all software applications that might need to be reinstalled and/or reconfigured. Sometimes it's not a matter of any data being lost, it's just a matter of the service having failed due to corruption or hardware failure. The data might reside in an entirely separate location, so you just need to get the servers back up and running. As it would be when dealing with anything that might occur to disrupt your services, there can certainly be incidents that just aren't anticipated. But the general idea behind recovery and restoration is to try to identify as many ways as possible that anything could fail. Then implement some kind of measure to ensure that you're able to recover from that failure. So the more you plan and prepare for such events, the more likely it is that you'll be able to recover from them successfully. So in this course, we've examined basic concepts surrounding authentication and disaster recovery. We did this by exploring the AAA Framework and Authentication Methods, passwords and PINs, software and hardware tokens, biometrics and authorization in the AAA Framework, non-repudiation, fault tolerance and high availability, fault tolerance and data activities, storage location and contingency planning, and understanding disaster recovery and the process of recovering from disaster.